Well, I'm Juan Zurita. First of all, I want to thank the organizers for this opportunity. And I'm going to talk about topology and interactions, about how to simulate the Creutz-Hubbard ladder in a photonic system. And this work was made along with Charles Crefeld from Universidad Complutense de Madrid and Gloria Platero from Instituto de Ciencia de Materiales de Madrid. Well, as we have seen several times during this conference, we can simulate a quantum system in a photonic lattice using classical light. For example, in a waveguide lattice, we can do this because of the mapping that exists between the partial wave equation of classical light and the Schrödinger equation of a single particle. In this case, the direction along the waveguide would act as the time of the quantum system. And of course, we can implement gauge fields in these kind of systems using either the geometry of the lattice or using some external field. And for example, these are two examples in which the geometry of the lattice is used to implement a gauge field, a magnetic field in this case. And we can, here, what they did was to include a waveguide with a very specific refractive index to change the phase of the hopping. And then in this one, what they did was to curve all the waveguides to implement the same magnetic field. And they also introduced an on-site energy, an on-site periodic energy, which would be the modulation by an external field, right? And even though this equation is just a single particle equation, we can use a trick to simulate several particles. For example, we can simulate two particles in 1D with a 2D photonic array. If we rearrange the degrees of freedom and use one of the coordinates in the 2D array to simulate the position of one particle and the other dimension for the position of the other one. In this case, we would be simulating bosonic particles because we are choosing a symmetric wave function. And this is the first time this was suggested was in 2011, but it has been implemented experimentally many times since then. And another very important technique is that the use of synthetic dimensions in photonic lattices, because you can have your physical dimension, but you can also have synthetic dimension using, for example, the modes in the waveguides. This was implemented last year in a 2D system in which the vertical direction here is synthetic. And it was also proposed for several different lattices in 3D. And these advances and many, many more have caused an explosion in topological photonics because there are now many systems that can be implemented experimentally that before they could not. These are some of them, but there are many more. And our work focuses on this topological insulator, which is the Creutz ladder. It's a quasi one-dimensional tight binding model. It consists of two legs of sides with these hoppings between them and a magnetic flux of phi between through each plaquette. And in this system, there's a very interesting phenomenon that happens, is that when the magnetic flux is equal to pi and m is equal to 0, m was the vertical hoppings, then we have the localization of all the states in the system. This is called a Aharonov-Bohm caging and is caused by the destructive interference caused by the magnetic field. And if we start with a particle totally localized here, we can see that the changes in phase, which we have represented with color here, will make the particle only go to the first neighbors, and then it will go back to the initial site because it cannot go any further. This has been seen in several experiments, and this is one from 2018 in a waveguide lattice in a rhombus chain. And this is how it would look like in the Creutz ladder, right? This is an exact diagonalization simulation. Again, we're using color to represent the phase. And we see this kind of breathing movement, right, between the initial site and the first neighbors. And I said that this system is a topological insulator. And here we have the topological phase diagram. This phase diagram is periodic in phi with period 4 pi. And each of the phases are labeled by its topological invariant, which is the winding number nu, which can be 1, -1, or 0. and is proportional to its Sag phase. And when m is greater than 2j, the system becomes trivial, and then the topological edge states, which are in the middle of the gap, go into the bulk bands, as we'd expect, right? Because of their bulk boundary correspondence. And these are the shapes of the edge states. These are simulations. And this is interesting because when m equals 0, all the edge states are completely caged in the two first sides of the ladder. And for the bulk states, this only happens when phi equals pi. But for the edge states, it happens for any value of the magnetic field as long as m is 0. If you switch on m, you change the conductivity of the lattice, and then you break what is needed for there to be this kind of caging, and then you get just the normal kind of edge states. And this system was very recently implemented. These two groups implemented a Bombas chain in a photonic lattice in two different ways, and they measured the Hartnett-Bohm caging. And one of these groups suggested that using very large on-site energies in the middle sites, they would essentially get a Creutz ladder. And we also have this also very recent implementation in cold atoms, where they used actually a synthetic dimension to do the different legs. They used the s and p orbitals in rubidium atoms, and they measured the momentum distribution, and it coincided with the theory of what they expected to be in a Creutz ladder. And well, we have included in our work, we are studying the Creutz-Hubbard ladder, which means we have included some interactions, Hubbard on-site interactions, and we will be considering bosonic particles. And this puts the system in the intersection of topology, interaction, and flat bands, which are three very interesting avenues of research right now, right? And we are going to study the two particle spectrum, the two boson spectrum, in the highly interacting regime with U much greater than J. What happens here is that the spectrum of the system will divide into two subspaces, the singly occupied bands and what is called the doublon band. And this name is because if the system starts in this subspace, the two particles will always propagate together through the lattice. Because in this model, there is no process that can make you lose all the energy to go back here. And this makes the two particles in a quasi-particle, which we can call a doublon, and these are its creation and annihilation operators. And in real systems, of course, there will be eventually dispersive processes that will make the doublon collapse. But doublons have been observed and have a certain lifetime. So during that lifetime, this holds. And using what is called the Schreiber-Wolff transformation, we have obtained an effective doublon Hamiltonian for that subspace. And we have obtained that the Hamiltonian is just a Creutz ladder Hamiltonian with renormalized parameters, which are these ones here, a chemical potential in the ends of the ladders, and a global shift. These renormalized parameters, we can see, for example, that the magnetic field is twice the original one, and that's because the charge of the doublon is twice the charge of the single particle. And the bulk topological phase diagram looks like this, which is very similar to the single particle one because it's just, it's very similar. But this chemical potential breaks the bulk boundary correspondence. And now the topological edge states of the system go into the lower band. This is the spectrum plotted against the magnetic field with m equals 0. And there are some edge states which are not topological that also appear. This is what these states look like for pi halves, which is the point where the particles will be caged now, where the doublons will be caged. And if we want the topological edge state to go back into the middle of the bulk, we can do that by compensating the chemical potential in the edges artificially. And the question we ask ourselves is, could this be simulated in a photonic lattice? And well, first of all, these are two particles, right? So we would have to do the trick of the two particles we saw before. And we see that if we do the product of the two Creutz ladder, one symbolizing the position of each one of the particles, we would get this lattice, this kind of weird 2D lattice, where these hoppings, these brown and orange hoppings, would have to be implemented between all the different plaquettes. It can look, well, for example, in this field blue sides will mean that the first particle is in state B and the second particle is in state A, right? And this like that for 4 sides. And this lattice can look a bit complicated, but it can be much clearer if we organize it in 3D. And we get this model here. This would be the unit cell of the lattice. And our idea was that using synthetic dimensions, like these ones in the article that I mentioned earlier, it could be possible to implement this model with all these different hoppings, because these hoppings in this lattice are because of the geometry that this group chose to do their waveguides. But changing the geometry would also change the hoppings. So in principle, we could do something like this. And here are some interesting phenomena accompanied by some simulations. And here I'm using color. The intensity of the color is the occupation number, and the hue is whether if it's more probable to find a single particle or a doublon in that site. So blue will mean a single particle and purple will mean a doublon. This can be measured with this, right? With this quantity over here. And some phenomena that we can explore in this system would be the caging of a doublon, which, as I said before, will happen now for pi halves because it's now double the charge, right? And it would look like this, and in the photonic lattice, it would look like this, right? This is the initial state, and then it will go to these sides, but always in the diagonal because we're still talking about a doublon, and these are the doubly occupied sides. And we can change the value of the magnetic field, and then the doublon will not be caged anymore and will propagate along the lattice. And we can see what it will look like. And we see that it's still only in the diagonal of the system because it's still a doublon, but now it goes through all the diagonal. And we can also have a doublon collapse. In this simulation, we have lowered the interaction to see what doublon collapse would look like. It would look kind of like this. We see that this is blue now because it's no longer a doublon. Now there's a probability to find single particles too. And we can see here what it would look like in the photonic lattice. We have to take into account that we are using double the sites that we need for the singly occupied sites. So it looks like the diagonal is kind of more occupied than it would actually in the Creutz ladder because it goes through both sides, right? And of course, we can also study the edge states of the system, both the doublon edge states, the topological and TAM edge states. These are the topological ones. This is the topological one. And of course, the single particle states too, and we have them here. So in conclusion, recent advancements in photonics are allowing simulation of quantum systems of growing complexity. The Creutz-Hubbard ladder is arguably the simplest model with non-trivial topology, flatband dynamics, and interactions, and it could be simulated in a photonic system using synthetic dimensions. Thank you for your attention. If you have any question.
Well, yes, thank you very much for the talk, and thank you for being on time. Yes. So we have time for maybe 2 small questions, or better 1 small question. Okay. Yes, please raise your hand and ask. Well, okay, let's start with 1 small question from me. On your slide number 5, there was a time running backwards. Well, you didn't show it for a long time, but I had the impression it was in the beginning.
Yes.
Yeah.
This is because
so the question is why?
because I searched in the Web of Science for all the papers that included the words topology or topological or things like that, start like this, and photonic, and the graph was like this. That's the only reason.
I see. Well, then a serious question actually. Did I understand correctly that when you have these doublons, for them, because of some reason, you have only term states which are in the gap, whereas the topological edge states are rather in the bulk. Is it true? I missed some. Maybe it's only under some. Yes, in this figure. Yeah.
Yes. What we found is that for m equals 0, which is this.
It's only well, but m equals 0 is also necessary.
Yeah, wait. I'll explain. You will have the topological edge states for the doublon system in the lower band always, if you don't compensate for the chemical potential.
Yes,
right?
this
and you have these term edge states. But what we have found is that for m equals 0, these edge states somehow they don't lose their form. They are still just like the regular edge states, which is a bit weird, but it might be related to this caging thing, right?
You mean they are localized even though they are resonant with the states, but still they don't propagate because of the caging?
Yeah.
Okay, I see.
If you compensate the chemical potential, you will always have them correctly. So if you want them back, you can do this.
I see. Well, thank you very much. Are there some other questions? Please raise your hand. Otherwise, we will go on. 1, 2, 3. No questions. So let's go on to the next talk. Thank you once again.